So in this video, we're going to define the derivative at a point and then go through an example of actually calculating this derivative for a particular function. So the derivative, as I said previously, is just another name for slope. So we already know a lot of names for slope. The instantaneous rate of change of a function at x equals a means the same thing as the slope of the tangent line to f of x at x equals a, which means the same thing as the slope of the function at x equals a, and now we have another name. It means the same thing as the derivative of f of x at x equals a. So derivative just means slope. The derivative of f of x at x equals a is the slope of the function f of x at x equals a, which is defined to be the slope of the tangent line to f of x at x equals a, which is the same thing as the instantaneous rate of change. And we just saw a video about what that instantaneous rate of change means, and that kind of gives us an idea about how we can calculate that instantaneous rate of change. So in the previous video, when we were calculating the instantaneous rate of change of f of x equals x squared at x equals 3, we were really calculating the derivative of f of x equals x squared at x equals 3. Derivative just means slope, which means instantaneous rate of change. So again, the derivative of f of x at x equals a, we use this notation f prime of a. So when you see that prime, it means derivative, which means slope. So it's the instantaneous rate of change of f of x at x equals a. Graphically, that's the slope of the tangent line to f of x at x equals a, and sometimes we just call that the slope of the function to f of x at x equals a. So all of those highlighted things were the equivalent statements that we had written on the previous slide, except for now we've added a notation that we use this prime to mean derivative. So f prime of a to mean the derivative of f of x at x equals a. So we've actually already discussed in the previous video how we can find it, because we saw that we could just look at the slope of the line that goes through the function at x equals a, and again at x equals a plus h. So that's f of a plus h minus f of a for the change in the y, and then all divided by a plus h minus a for the change in the x's. That gives us the average rate of change, and then to get to that instantaneous rate of change, we need to let that distance h from a to a plus h, we need to let that go to 0. So we need to look at the limit as h goes to 0 of f of a plus h minus f of a, all divided by a plus h minus a. And that's going to give us the slope of the tangent line at x equals a, which now we know is the derivative of f of x at x equals a, and we write that f prime of a. And then all I did in the second expression was I just took a plus h minus a and simplified it. The a and the negative a cancel with each other, so that denominator, more simply, is just an h. So when we're actually calculating those limits, it's easiest to remember that the denominator just simplifies to be h. So the expression on the far right is really what people think of as the limit definition of the derivative, because we've defined the derivative as a slope and simplified. But sometimes it's nice to think about the expression in the middle, because it really lets you see that, oh yeah, I'm just calculating a slope, change in output over change in input, and then I'm taking the limit as h goes to 0 to let the 2 points that define my slope get closer and closer together. So then we can actually estimate this slope, this derivative, numerically. If we look at that expression for the slope, f of a plus h minus f of a over h, and then to take the limit, we just evaluated it at smaller and smaller values of h to find the limit. And by smaller and smaller, I mean values that get closer and closer to 0. So we need to let that h get very, very close to 0 to kind of see what's happening with the slope of the tangent line, which is the derivative. So in example 2, we're going to look at the function f of x equals 2 to the x and estimate the derivative of that function at x equals 4. And the notation for that is f prime of 4. So what we're estimating is the slope of the tangent line to f of x at x equals 4. So we're going to estimate it and make sure that our estimate is correct to 2 decimal places. And then we want to explain what our answer, what the answer we found means graphically. And we just said it's the slope of the tangent line to f of x equals to the x at x equals 4. And I'm going to work through this example as part of our kind of supplemental lecture that we missed because of the snow. But you can find another video example for a similar problem as video example 1 on As You Learn. So again, we're trying to estimate this f prime of 4, the derivative of f of x at x equals 4, which is the slope of the tangent line to f of x at x equals 4. We just saw a definition for the derivative in terms of, we're looking at the slope of the secant line and taking the limit as h goes to 0. So using the limit definition of the derivative, we know f prime of 4 should be the limit as h goes to 0 of f of 4 plus h minus f of 4, all divided by h. So now I need to simplify that numerator. I need to figure out what f of 4 plus h is and also what f of 4 is. So I have a formula for f of x. So to find f of 4 plus h, I just need to put 4 plus h in for x every time I see it. So f of 4 plus h is going to be 2 to the 4 plus h. Similarly, to find f of 4, I just need to plug in 4 for x. So f of 4 is going to be 2 to the 4th. So that limit that I need to calculate simplifies to the limit as h goes to 0 of 2 to the 4 plus h, that's f of 4 plus h, minus 2 to the 4th, that's f of 4, all divided by h. And then 2 to the 4 plus h, I can't simplify that because of the h. But 2 to the 4th, I know what that is. 2 to the 4th power is 16. So I can rewrite this limit as the limit as h goes to 0 of 2 to the 4 plus h minus 16, all divided by h. And then the expression that I'm supposed to be taking the limit of is as simple as possible. So my next step is to stick values of h that are approaching 0 into the function, make a table of outputs, and see what that slope, what that f prime of 4 is leveling out to as the h's get closer and closer to 0. In your notes, to kind of help you from copying all this down on the board, I had already included a table for these values of h that get closer and closer to 0. So I started with h equals 0.1. So remember that the expression I'm supposed to be looking at is 2 to the 4 plus h minus 2 to the 4th all over h. So if h is 0.1, 4 plus h is 4.1. So I'm looking at 2 to the 4.1 minus 16, because 2 to the 4th is 16, all divided by h, which is 0.1, and then when I put that into my calculator, I got 11.484. And then I did the same thing, replacing h with 0.01, so that 2 to the 4 plus h was 2 to the 4.01, calculated the expression and got 11.129. And I did that for each of those values of h's, and as the h's got closer and closer to 0, I could see that the slopes were changing less and less each time, each smaller h that I chose. And this is why I needed to keep making my h, keep a table and to see the slopes level off, as opposed to just putting in a small h and going with that as the slope, because I'd have to be correct to 2 decimal places. So that means my answers have got to match for 2 small value of h and then a smaller value of h for 2 decimal places for me to know that I've gotten a small enough h to really capture what that limit is going to be. So for 0.001, when I evaluated the expression for the slope, I got 11.094, and for 0.001, I got 11.091, and so to 2 decimal places, those are both 11.09, so I think I've gone far enough. And the h, I could approach from the right, like we drew in our picture, but I could also approach from the left. I could take h's that were negative, so that my second point was to the left of my original point, and do the same thing. So I just showed you h is negative 0.1, negative 0.01, negative 0.001, and negative 0.0001, evaluating them in our expression for slope. And we see that we also level off at 11.09. So our slope, our derivative, is 11.09. You can note that if we look at this graph, we can see that there's just going to be one tangent line at x equals 4. Because there's only one tangent line, the limit as our h's get close to 0 from the right, which is our first column that we did, and the limit as h goes to 0 from the left have to be the same thing, because they're both going to give us the slope for the tangent line. So our limit from the right, which if you remember from pre-calculus, there's a little plus to indicate that you're coming in from the right, was 11.09. That was our first columns of work. And our limit from the left was 11.09, and that was our second column of work. Because from the graph we know that there really is only the one tangent line, then we probably could have just found either the limit from the right or the limit from the left and known that the other one was going to be the same. So when you're working through it on your own, I'm totally okay with you just giving that first column of data to say that this is the limit. If you know that the function goes smoothly through the value of x that you're interested in this case through x equals 4, so there really is going to be just one tangent line. So in summary, we discovered that the derivative of 2 to the x at x equals 4 is 11.09, and then remember that what that means graphically is that 11.09 is the slope of the tangent line to f of x at x equals 4. So we could have drawn in a tangent line and estimated its slope, but because we needed to be correct to 2 decimal places, we needed to do this thing with a limit and plug in small values of h that were getting closer and closer and closer to 0 so that we could see numerically what the limit was approaching. But we can still use the graph to kind of help us check the reasonableness of our answer. 11.09 seems reasonable for the slope of that line. If I had gone through this work and I got 0, I would know I'm wrong because 0 is the slope of a horizontal line, and the line that I drew is definitely not slope 0. Not horizontal. If I got a negative number, I would know I was definitely wrong because that line clearly is increasing, and so it should have a positive slope. So really realizing that the derivative that you're calculating using this numerical procedure is just telling you the slope is important. So now that you've finished finding this derivative numerically in the video, you can try practice problem number 1, which asks you to basically do the same thing for a different function. And that'll help you know if the ideas in the video have kind of made sense to you.